This is the answer key for the Pre-Calculus Unit 6 Test Review Guide. This first question asks you to use the vertical line test to determine if each graph is the graph of a function. Remember that the vertical line test asks you to consider a vertical line that can be drawn anywhere on the graph space, vertical meaning up and down, and if that graph can, or if that line can touch the graph of the relation more than one time anywhere. It could be there, it could be there, and so on. If there's anywhere where the vertical line can touch the graph more than once, then that is not the graph of a function. But if throughout the entire function there's nowhere where a vertical line can be drawn that would touch the graph more than once, so in this graph every x value has its own y value, no x value has more than one y value, then that is the graph of a function. So those should be circles and not diamonds. I don't know what I was thinking when I made that graph, but it does fail the vertical line test at x equals 2 and only at x equals 2. But if you were to draw a vertical line, x equals 2 has two y values, and therefore no, it is not a function, the graph of a function. In this graph, it would fail the vertical line test near the middle, either here or here or here or so on. So the answer there is no. And in this last graph, there is nowhere on the graph where the x value has more than one y value, and therefore this graph, yes, is the graph of a function. Now, for these next few problems, you're evaluating a function given in function notation for certain x values or for certain expressions. So you're going to use substitution here to do these computations. So for example, in part A, Roman numeral 1, you're going to multiply 2/3 times -12 squared plus 5. Make sure that if you're typing that into a graphing calculator that you use parentheses. And when you do that, you should get positive 101. In number 2, 2/3 times -x with parentheses squared plus 5, and that negative x squared becomes positive x squared, so that equals 2/3 x squared plus 5, which by the way is exactly the same as the original function. And then in this last part, you're going to substitute the whole x plus h, so 2/3 times x plus h squared plus 5. Now, x plus h squared, you might want to pause this and FOIL x plus h times x plus h, and you get x squared plus 2xh plus h squared plus 5. And I ran out of room for what you're going to get there. Then I guess I'm going to go over, let me put the answer over here just to make space for the other problems. And so what you're going to get here is going to be 2/3 x squared, and then the 2xh times the 2/3 is going to give you plus 4/3 xh plus 2/3 h squared. You distribute that 2/3 But then that 5 doesn't have anything multiplied by it, so it's just going to be plus 5. And so this big ugly thing is your answer for part 3. In letter B, excuse me, 4 minus 3 radical 12. And then if you look just at the radical 12, that can be simplified, and of course you should always simplify a radical. If you think about that, 12 is 2 times 2 times 3. And so that whole thing then becomes 4 minus 3 times 2 radical 3, which is 4 minus 6 radical 3. In this next one, 4 minus 3 radical negative x. And because you have a negative inside of a radical, that'll be 4 minus 3i radical x. And then this third one can't be simplified, so it's just going to be 4 minus 3 radical x plus h. And in letter C, part 1, I'm going to substitute negative 10. Negative 10 plus 1 is negative 9. 3 times negative 10 is negative 30. And that whole fraction simplifies to 3 over 10, and it's positive. In the next part, it'll be negative x plus 1 over negative 3x. And you can have that as your final answer. It is completely simplified. It just has negative leading coefficients. But if those negative leading coefficients bother you, you can factor out, the thinking would be to factor out a negative 1 from the top and factor out a negative 1 from the bottom. And then you could, if you wanted to, give your answer as x minus 1 over 3x. And in that case, I would accept either answer. Okay, doesn't matter, this or that. And then finally, for the x plus h, you're going to have an expression that can't be simplified beyond what your original substitution is. So x plus h plus 1 over, well, yeah, I guess it can be. So 3 times x plus h, and then you want to distribute the 3. And the answer key I had written on paper, I had done the distribution before I wrote the answer. So x plus h plus 1 over 3x plus 3h. And that's it. Done. Now, in number 3, you want to give the domain for each of these. And remember, maybe you want to make a note to yourself off to the side here. Remember that there's only 3, let me write this out for you, 3 things that restrict a domain. And it's only these 3 things. There is no other thing that will affect the domain to exclude x values from a domain. And the first is you can't have a denominator equal to 0. Cannot equal 0. The second thing is that you cannot have a square root. Cannot be of a negative. And the third thing is that you cannot, the logarithm cannot be, my English here is not all that fabulous, but you're getting the gist. Logarithm cannot be of a negative or zero. There's absolutely nothing else that exists that would restrict a domain. And so when you look at a problem like letter A, 3 minus 5 to the x plus 1 power, there's no denominator, there's no square root, there's no logarithm, and because of all of that, your domain is going to be all real numbers. But in part B, your function here has a denominator, and so you want to think to yourself, well, I can't have a denominator equal to 0, so 2 minus x cannot be equal to 0, which means that 2 cannot be equal to x. I just solved that equation. And so my domain would be all numbers except for the value x equals positive 2. So negative infinity to positive 2, and then positive 2 to positive infinity. This is the graph that goes with number 3b, and that's f of x is equal to, and then the fraction 5, and then you want to type the slash 5 over x, or I'm sorry, 2 minus x, and in your phone or in your tablet, there's you just type the divide sign, and in a laptop like I have here, you would hit the slash key for divide. That should be fairly intuitive. And the question is asking about the domain, and you want to kind of figure out the domains algebraically, and so I've got that in the other portion of the video, but just so that you can see that the x value that's missing, if you can kind of follow along here, you can see that the graph has an asymptote at x equals 2, and so x equals 2 is the value missing from the domain. In part C, again, I can't have a radical or a square root of a negative number, and so here I'm going to be thinking to myself, that 2x minus 1 must be greater than or equal to 0. You can have the square root of a 0, and so 2x minus 1 can equal 0, unlike the logarithm where it cannot be 0. The square root of 0 is just 0. But then in this case, 2x would have to be greater than or equal to 1. Divide both sides by 2. X would have to be greater than or equal to 1/2. And so for this function, x is greater than or equal to 1/2, so it would include the 1/2 because of the or equal to, and for x to be greater, it would be all numbers from 1/2 all the way up to positive infinity. Number 3c, and I don't think I said this for 3b, but you don't need to type the f of x. You can just type the expression, and that'll give you the same graph. I'm typing f of x because it's on the paper, and sometimes if you've got several functions that you're working with, it helps you to sort them out if you identify f of x and g of x or whatever. So here in your device, your phone or your tablet, you have a square root key. Because I'm typing on a laptop, it's just as easy to type SQRT, and that automatically changes it to a square root. and then I've got 2x minus 1, and then I have to hit the right arrow to get outside of the square root, and then I'm going to type plus 3. And the question is asking about the domain, and you can see here that the domain starts at this endpoint right there, and that x value is 1/2. Sorry, my notifications are coming up on the screen. So that x value is 1/2, but it's included. There is a point at 1/2, but there's no points to the left of 1/2, and so your domain starts at 1/2. I know that it says 0.5, but remember I don't want decimals there, so it starts at 1/2 and goes to positive infinity. In letter D, remember that the logarithm, the numbers that are put into the logarithm have to equal a positive number, so you want 3x plus 2 to be greater than 0 but not equal to 0. So 3x has to be greater than -2, and then x has to be greater than -2/3. And therefore your domain for part D is going to be -2/3 to positive infinity, but not including the -2/3. So use the round parentheses, not the square bracket for the -2/3. This is the graph that goes with number 3D. And again, I'm going to include the f of x. You don't have to. And this time I'm going to start by typing log, and if you're in your device, you go under functions, and it's in the miscellaneous functions. Make sure that you don't use a log with a different base for this problem, because it doesn't have a written base, and therefore you assume that it's the common log or log base 10. We'll get more into logarithms in Unit 8. And here it says log of, and then the quantity 3x plus 2. And here you can see that there is an asymptote, and that asymptote would happen where 3x plus 2 is equal to 0, which is going to be -2/3. And so this asymptote is at -2/3. And if you look at the values, the point values, they just get closer and closer to -0.66666666. And most graphing softwares have trouble when you get close to an asymptote, and that's about as far as you're going to be able to drag it. But remember that that 6 in the x value repeats forever. In letter E, again, remember that what's inside of a radical, it has to be either positive or equal to 0. So you want to think here that 9 minus x squared is greater than or equal to 0. 9 has to be greater than or equal to x squared. Take the square root of both sides. Plus or minus 3 has to be greater than or equal to x, and that's technically the absolute value of x. So really the thinking here is from -3 to x to +3. So x is between -3 and +3. And the way that you would write that, including the -3 and the +3 in interval notation, would be -3 to +3 with square brackets. This is the graph that goes with number 3E, and so we've got f of x is equal to, and now you've got a square root of 9 minus x to the second power. If you're typing on a laptop, you can do Shift-6, and that gives you that little caret, and you now have to the second power. And notice that algebraically we said that it's -3 to +3, and if you look at this graph, it does have a value at -3, and it does have a value at +3. And so the domain is all the values between -3 and +3, including those two numbers. Now in this last one, part F, you have to consider both the radical in the numerator as well as the denominator that can't equal 0. So I'm going to do this in two steps, I guess. I'm going to start with the numerator, and my thinking here is that 8 minus x has to be greater than or equal to 0. So 8 has to be greater than or equal to x. And if it were just that, that would be 8 is bigger than x, so that would be negative infinity to 8 inclusive. But that's if it were only the radical in the numerator. Let me highlight that for you. So if it were only a radical and there were no denominator, your domain would be negative infinity to 8, including 8. But you also have to consider that you've got the denominator, and the denominator can't equal 0. So here you are thinking that x plus 3 cannot equal 0, and therefore x cannot equal negative 3. And so this number, negative 3, is somewhere in between negative infinity and 8. So your domain is going to end up being all the numbers from negative infinity to 8 except negative 3. So the way you write that then is from negative infinity to negative 3, not including negative 3, and then from negative 3 to 8, and yes, including 8, because there was that half equal sign over here with the x's. 8 is greater than or equal to x. Number 3f, and so we'll say f of x here equals, and then I've got the square root of 8 minus x. I have to right arrow so that I can do divide then, and in the denominator, x plus 3, and then let's make this stand out with a brighter color. So here, notice that you've got an asymptote here at x equals negative 3, and that's because negative 3 would make a denominator 0. Remember that when it comes to denominators, which we'll talk more about functions that have an x in a denominator more in Unit 7, when you have a denominator, if it's not a whole, it's an asymptote, and a whole only happens when a factor cancels. So in this case, you've got the asymptote at x is negative 3, and the numerator, 8 minus x, has to be greater than or equal to 0. And so you want all the numbers from negative infinity to positive 8, which is right there. Of course, not including that negative 3 from the denominator. But if you want to look and see that that's positive 8, just kind of drag. I'm running out of mouse trackpad. But kind of drag over to there. So the 0.8 comma 0 is included because 8 just makes the radical square root of 0, which is fine. That's not a restricted domain, but anything bigger than 8 would give you the square root of a negative number. So you're going to do 8 with a bracket as the upper end of your domain because there won't be any numbers bigger than 8, but we do include 8. And now for these last few problems on the first page, you're going to use the graph and come up with interval notation for the domain and the range. So here our domain is going to be all real numbers. Remember that if the graph goes to the edge of the graph space, you can assume that there are arrows there. And in this case, this graph stops. Now when I'm talking about the range, in this case, the graph stops at the top, which is positive 5. And remember that your range always goes from bottom to top, in this case negative infinity to positive 5, and it includes positive 5. So your domain is always left to right, and your range is always bottom to top. There's always going to be whatever number is smaller is the first number you write, and whatever negative infinity is smaller than any other number, and then whatever number is bigger is going to be the second number that you write. So the first one, domain is all real numbers. The second one, the range is negative infinity to 5. In letter B, the domain has some x values missing in the graph right in here in the middle. And so the domain is going to be negative infinity to negative 1, and it touches negative 1. And then it starts up again at positive 1, including both negative 1 and positive 1, and goes to positive infinity. Now, if you look at the range, the graph on the bottom has y values all the way down to negative infinity, but at the top, it stops there at y equals 0. And so my range is going to be negative infinity to 0, including 0. In letter C, as I follow the x values from here to here, then there's some space there, and it goes forever to the right. My domain's going to therefore have two different sections. And I'll start with the section over here, and that goes from negative 5 to negative 2. But there's that open circle at negative 5, so it's going to be round parentheses, negative 5 to negative 2 with a square bracket because of the closed circle here at negative 2. And then from negative 1 with a closed bracket all the way to positive infinity, all the way to the right. And that's your range. And then I'm going to erase all of that, all my scribblies on the graph. And to find the range, then the very bottom value of the graph is negative 5. Yeah, so that was my clock. When I make the videos in my living room, that's what happens. Let me start the range again here. So the range starts at the bottom with the y value of negative 5, and it touches negative 5. But notice that over here, there's no y values missing, all the way up to positive infinity. This doesn't matter because those y values happen over here. Hang on a second, those y values happen over here, so it doesn't matter that they're missing over here. And if you really just think about this whole graph as going from the bottommost part of the graph to the topmost part of the graph, these two places aren't missing y values because of that. So the bottom of the graph is and includes negative 5, and it goes up to positive infinity and is not missing any y values. And then in this last graph, there's that pesky hole in the graph over here, and that hole would have an x value of 6 and a y value of negative 5. So those numbers are going to be missing from the domain and from the range. And don't forget that there's an endpoint. This would be a square root equation, but it's got that hole in it. So let's say here that our domain starts at negative 3, the x value negative 3, and it includes negative 3, and it goes to here before it misses that hole, so that's negative 3 to positive 6, not including positive 6, and then it goes to positive infinity. And then the range, and again I'm going to erase Sure I am. The range, gotta love technology. The range then here starts at the bottom of the graph at negative infinity and goes up, but there's that hole there, and so it goes up to -5, not including -5, and then goes from -5 to that tip top part of the graph at y equals 1, and it includes 1 because that's where the end point is. So this next page is all about the piecewise functions. So let's take a look, first of all, at a piecewise graph that's given to you and see if you can use x values to pull out y values. And you kind of want to look at each section of the graph. Over here, these are all the numbers that are going to be less than, but not including x equals -2. Then that part in the middle is going to be all the numbers including -2 to +3, including both -2 and +3. And then this last piece, let's do this one in blue. Well, maybe not blue. Yeah, blue. Would be from +3, not including +3, on to positive infinity. And what I like to do then is kind of decide each of the questions that are being asked, where does that number fall based on the different colors. And so, for example, -6 falls in that section of the graph that that is the x value that falls in that section of the graph that I colored with green, and so does -4. But then -2, remember, is the one where the graph changes, and so if I look at where x is equal to -2, it's a closed circle there, and so that question for part C is going to be the pink part of the graph. So also is 0, that middle part of the graph that I shaded pink, and so also is x equals 2. And then again, the question is about x equals 3, because right here where x is 3, oh look, we've got the closed circle again on the pink section, and so that's also going to be from the pink section. But for all the numbers greater than 3, we're going to be looking at the blue section, and so both part G and part H are going to be taken from the blue section of the graph. So start by making sure you understand where we're pulling those numbers from, and then to answer the questions, f of -6, that means where x is -6, the y value is +5, where f of x is f of -4, so that's going to be right here, and the y value is 0. When x is -2, all those points along that line that I shaded pink are 4. So f of -2 is 4, f of 0 is 4, f of +2 is 4, f of 3 is +4. And then in the blue section, where x is 4, the graph is -2. And where the x is 5, the graph is +1. Now in this next section, again, I want to keep track of which piece of the function we're looking at, but this time I'm not giving you a graph, I'm just giving you equations. So I'm going to start just for myself to color code the different sections, and I'll do all the x values less than -4 with pink, all the x values from -4 to 2, including -4 but not 2, I'll do that with green, and then all of the numbers greater than or equal to positive 2, I'll shade with blue. And so when I look at the questions being asked below, -7 is less than 4, and -4, sorry, and therefore it's from the pink section. But -4 is equal to -4, and notice that the equal sign for the less than or equal to -4 is in that green section, and so I'm going to use the green part of the formula or the function equation to find f of -4. -2 is in that same section, 0 is in that same section, and 13, because there is no or equal to sign there, so this one does not have the or equal to sign. Therefore, f of exactly 2 is going to be from that bottom or the blue piece of the equation, and so is 5. So when you substitute for x is -7 in the pink section, this first part you should get 31. When you substitute -4 in the middle part, you should get positive 64. And if you think about this one, when you type that into your calculator, -x cubed, -4 cubed, the -4 cubed is going to be -64, and then you've got this extra negative, so that'll make it positive 64. Make sure you track with that, or that you can type it into your calculator, but it will be positive 64. F of -2 is 8. F of 0 is 0. F of positive 2, then now we're looking at the blue section. F of positive 2 is going to be 13. And F of 5, 3 times 5 squared, 3 times 25 plus 1 is going to be 76. Again, I'm going to use shading for this next problem, and I'm going to shade the first piece of the equation or the function pink, and then the middle section or the middle piece I'm going to shade green, and the bottom one I'll shade blue. And looking at the numbers that I'm asked to evaluate for, -19 is in that first or the pink section, but because of where the equal sign is, -5 is in the green section, so is 0, so is positive 4, and because there's an equal sign there, so is positive 10. So positive 10 also gets that green shading. And then the positive 12 is in the section that is greater than 10, and so that gets the blue shading. So when you substitute in, for the pink section, all the answers would be -15. When you substitute -5 plus 6 inside of a radical, the square root of 1 is 1. When you substitute 0 into there, 0 plus 6 is 6. And leave the answer as an exact answer, which means that it's radical 6, not the decimal rounded answer. Same thing with f of 4. 4 plus 6 is 10. You can't simplify radical 10, and so it's just radical 10. And then 10 plus 6 is 16. So in this case, you're going to say, oh, I recognize that the square root of 16 is 4, and so your answer for part 5 has to be 4. And then in 12, or in part 6, you're going to substitute the 12, so 2 over 12 plus 8. Well, 2 over 12 is 1/6, and if you have a number smaller than 1, added to a whole number. When you're talking about fractions, it's just going to be 8 1/6. For number 7a, and remember that when you're typing in piecewise functions, you want to use the curly brackets. And so on a laptop, I'm going to come down here and get my alphabet from there. I'm going to start with the absolute value. You can also type ABS and then parentheses on a laptop. I like to actually see the goalposts. So I'm going to type the absolute value key, and then I'm going to type the x plus 4, and then I'm going to right arrow over to get outside of the absolute value, and then -1. But I want to restrict that excuse me, to the portion of the graph that is less than -2, but not including -2. So I'm going to go over here and grab the curly brackets, and then I'm going to go back here and I'm going to type x is less than -2. And you can see that the graph then stops at -2, and it doesn't include -2. It tells you that the y value is undefined when x is -2. Then the next piece of the graph is, now this is where your Desmos isn't going to graph a point. You're going to graph a dot on the graph, but if you wanted to type it in, you could type it the same way, where it would be 1. I'm sorry, this is not going to be a dot. This is going to be a horizontal line. It's letter B that has a dot in it. So anyway, in A, type the 1 and then grab your curly brackets, and then go back to type in your -2 is less than or equal to. Oh, and another thing about Desmos, if you wanted to type less than or equal to without using the keys down here, if you just on your keyboard type the less than sign and then type the equal sign, it changes the less than to less than or equal to. So -2 is less than or equal to x is just less than 3, and that gives you your horizontal line here. And notice that the horizontal line is defined at -2, 1, and that happens to overlap with the absolute value piece of this graph. And then the third part of the graph is the quadratic, so negative, and then parentheses x minus 5, caret squared, right arrow to get down again, and then +3. I'm going to grab my curly brackets here and say that that's strictly for when x is greater than or equal to +3. And so over here in the graph, you see that the graph does have a discontinuity here. It doesn't connect where x is 3. The function is defined at x equals 3, y is -1, not up here. X is 3 is undefined at +1, but it's defined at 3, -1. Now for the graphing section, I'm also going to color code the pieces of my graph, just so that you can kind of track along with what I'm doing here. So I'll make the piece of the graph that is less than -2 pink, and then I will make the piece of the graph that is between x equals -2 and x is 3 green, and finally the third piece of the graph that's the numbers greater than 3, I will make blue. And so the first part, the pink part, is the section of the graph that's the absolute value, and it's, you understand the transformations. This is a shift to the left of 4 and a shift down of 1, and there's no vertical stretch or compression. And so I'm going to move the vertex of this graph to the left 4 and down 1, and then the slope is +1, and my graph, the absolute value portion of this graph goes to x is -2, and so this part of the graph that you should be using a straight edge for should look something like that. And this graph is Interesting, because then this next piece of the graph, the x, from x is -2 to x is 3, even though it includes, because of that equal sign there, it includes x equals -2, it's 1, and that's where the graph is from the first piece of the equation. And so I'm just going to fill in that point at x is 1, and then that goes to +3, and it's just a constant, it's a horizontal line to x is +3, right there. And so if you're drawing with your pencil, that section of the graph, where it goes from pink to green, just overlaps, and there's no open or closed circle there. It's just continuous. There's no break in the graph there. The first time there's a break in the graph is at x equals 3. And then the last piece of the graph, the blue piece of the graph, is quadratic, and that's, if you look at the transformations, you've got a flip, and you've got a shift to the right and a shift up. So it flips over the x-axis, and so the vertex of the graph is shifted to the right 5 and up 3. So there's the vertex of your graph, and then your quadratic graph, and you'll probably need to use your calculator for this. The shape ends up looking kind of like this, and it'll end here at x equals 3, or it begins, if you're going from left to right. And so there's a closed circle right here, and then on this other end it goes to infinity. Now remember that when you're drawing your graphs on your test, even though Desmos or the graphing calculator doesn't show open and closed circles, it's pretty important on your test that I see where the circles are open and where the circles are closed, and that you show that those values of the graphs in that way. So there's your first graph. And then in the second, number 7b, another piecewise graph. And so we'll start with the x minus 1, and I'm going to grab my curly brackets here and say that that is for when x is less than -2. In the second part, this is the one that Desmos won't graph the point if you type it in with the curly brackets. You could, if you wanted to, type parentheses like an ordered pair, -2, -1, and it'll graph that as a point. And you can do all the same things that you do with that point that you do with the graphs of lines and other function families. And notice over here that the graph, the red part of the graph is not defined when x is -2, but the graph is defined at -2, -1. And then the third piece of this graph is the rational function 1 over x plus 2, and move to the right, and then I'm going to grab my curly brackets and say that that is for when x is greater than -2. And let's make that green. So here I've got what would have been, if I graphed this and just this function without any restrictions on what I'm graphing, there would be an asymptote at -2. So that asymptote would be right here, and that's why the graph comes up real close to it there. It also would have a horizontal asymptote at y equals 0. So x equals -2 and y equals 0 are the asymptotes of the rational function part of this graph. There's your middle piece, and there's your linear piece. Graph here. Again, I'm going to color code it for you so that the first piece I'll have in pink, and the second piece I'll have in green, and that third piece then I will have in blue. And so the pink section of the graph, x minus 1 for all x values less than, but not including -2. So there's going to be an open circle here at -2, -3. So -2, -3, there's an open circle, and the slope of the graph is 1, and so those points kind of go like this. And if you were to think about it, don't draw this, but if you were to think about it, the graph of x minus 1 would hit the y-axis at -1 and have a slope of +1 and a y-intercept of -1. And so I'm going to get rid of all of that. And I wonder if the video will pick it up, because sometimes the video doesn't pick up what I undo. But anyway, just imagine continuing that graph toward the y-axis and think about the y-intercept. Now the green part of the graph is, again, a constant, and it's -1, but this time it's only 1 point. So it's at the value of x equals -2. The y value is going to be -1, I'm sorry. So at x equals -2, the y value is going to be -1, and it's just a point. And then last but not least, the rational function part of the graph has a vertical asymptote at -2. And so I'm not really wanting to draw it in here, but imagine that this is a vertical asymptote for the rational part of the graph, and it's got also a horizontal asymptote at y equals 0. And so the blue portion of the graph then is going to be here, all the numbers greater than -2, but that also includes this part of the graph that goes up toward the asymptote. And so if you ignore the asymptotes, in fact, maybe I can go back and erase those asymptotes. So if you ignore the asymptotes, remember asymptotes aren't really part of a graph, and we'll talk about those more in the next unit. But if you ignore those asymptotes, then your piecewise function, I erased too much. Your piecewise function is just the pink and the green and the blue. Now for this next page, you're wanting to look at the even or odd functions, and we'll start with the graphs and then get into algebraically proving things. But just remember the concept of the even functions have line symmetry about the y-axis, not the x-axis, but the y-axis. And the odd functions have point symmetry of 180 degrees about the origin. And something that has x-axis symmetry isn't a function, and so we're only talking here about functions. And so make sure that if it's not a function, then it's not an even function or an odd function, it's just not a function. So in this first graph, if you look at the origin right here, this graph would spin around 180 degrees and it would appear unchanged. And so in that case, it has point symmetry about the origin, and a graph that, or a function that has point symmetry about the origin then is an odd function. And then for this one, this graph has line symmetry, and or you can think of it as reflection symmetry. And it's if you reflect the graph across the y-axis, it will appear unchanged. and therefore this has line symmetry over the y-axis, and therefore it's an even function. And then in this last one, when I look at this, the first thing I see is that I want it to have point symmetry about this point right here. But that's not the origin. That point is not the origin. So even though it probably has point symmetry, I would need to look at it a little bit more closely. It probably has point symmetry of 180 degrees about that point that I circled. That's not the origin, and therefore it has neither of the two types of symmetry that I'm asking for, and therefore it is neither an even function or an odd function. And so there you have three examples of even function, odd functions, origin symmetry, and y-axis symmetry. Now, for each of these next 6 functions, if I were you, I would also graph them as you go, and just take a look at the graphs. But I'm going to ask you to prove what you're saying about the symmetry or the even and odd functions based on the algebra. And so remember that to determine this algebraically, you are going to substitute negative x. So you're going to compute f of negative x. 9a, and we want to look, just visually inspect the graph to see if it looks like it has y-axis symmetry or point symmetry about the origin, or if it doesn't have either of those symmetries that we're looking for even or odd functions. So number 9a is x over x squared minus 16. And that looks to me like it's got point symmetry about the origin. Let me zoom out. And if you look right here at the origin, it's 0, 0, and consider the rest of the graph spinning 180 degrees. This section here would end up looking like that section there, and this section up here would look like this section down here. So we'll need to prove it algebraically, but it looks to me upon visual inspection like it is an odd function. So for example, here, if the given function is x over x squared minus 16, and you substitute negative x, that gives you negative x in the top, and remember your parentheses, negative x squared minus 16 on the bottom. And so f of negative x, when you simplify all of that, equals negative x over x squared minus 16. Now, if you think about that, the denominator here remains unchanged from the original function. But what you also want to notice is that the numerator is negated. And if only one numerator or denominator is negated in a function, that makes the whole function negated. And so here, in this case, f of negative x is equal to negative f of x. And that algebraically proves an odd function. That accompanies number 9b, and it's a square root of 10 minus x squared. And if we zoom in, I meant to zoom in, this graph, let me put this in projector mode, it's easier for you to see in the video. What you'll see is that it looks a lot like it has reflection or line symmetry over the y-axis. Here's the y-axis. And if you took this point, which is probably radical 10, and reflected it over to the other side, that certainly looks like it would be negative radical 10. And so again, we'll have to prove this algebraically, but it looks to me like it's an even function. In letter B, again, I'm going to compute f of negative x. So that's radical 10 minus, and then parentheses negative x squared. And when I simplify that, I get negative x squared is just x squared, and so 10 minus x squared, well, that's exactly the same as the original function, radical 10 minus x squared. So the function remains unchanged if you substitute negative x. So f of negative x is equal to f of x, the original function. And that is how you algebraically prove an even function. For number 9c, and the function is 5x to the 6th power, and then minus 3x squared, and then plus 2. And again, this graph looks like it is an even function. It looks like it has line symmetry over the y-axis. In this next example, I'll compute f of negative x equals 5 times parentheses negative x to the 6th minus 3 parentheses negative x squared, and then plus 2. And when you have an even power on a negative x, it keeps the same as the original sign, so this will become 5x to the positive 6 minus, and then an even power on negative x is going to keep the term with the same sign, so 3x squared, and then plus 2, and positive 5x to the 6 minus 3x squared plus 2. If that's what you get when you compute f of negative x, then you have proven that f of negative x is exactly the same as the original function f of x, and therefore that function is even. This will be the graph for number 9d, 7x to the 5th, and then plus 2x to the 3rd, minus 3x, and plus 1. And it's that plus 1 at the end that shifts the whole entire graph up and makes this, although it looks like it has point symmetry here, in order for the graph to be odd, it has to have point symmetry about the origin, and it definitely does not have rotational symmetry or point symmetry about the origin. It also doesn't look like it has reflection symmetry across the y-axis, so this is probably not an odd or an even function. For letter D, when I substitute negative x here, 7 times negative x to the 5th power plus 2 times negative x to the 3rd power minus 3 times negative x plus 1. Whenever you have an odd power on a negative x, the sign of the term changes. So now f of negative x equals negative 7x to the 5th minus 2x to the 3rd plus 3x, and then plus 1. Now here, the first sign changed, the second sign changed, and the third sign changed, but the sign on the last term did not change. That's still the same as the original function. And since the requirements for an odd function are that the whole function is negated or stays the same for an even function, in this case, your f of negative x does not equal itself, the original function I mean, and it does not equal a negation of the function, and therefore this one is neither odd nor even. This is the graph for number 9E, and it's x minus, and I'm going to grab the absolute value symbol here, absolute value of x. This is an interesting graph, I think, anyway. You may not. I'm kind of a math person like that. But you can see that on the negative side of the graph, the graph has a slope of 2, and it's a positive slope, whereas on the right-hand side, or the positive side of the graph, it's a horizontal line that has a slope of 0 and follows the x-axis. Thus, it doesn't have point symmetry about the origin, because if you rotate this 180 degrees, it won't end up looking exactly the same. And it also doesn't appear to have line symmetry across the y-axis. And so I would say that this function is neither even nor odd. Now this is an interesting one. When you substitute f of negative x here, your first term is negative x minus, and then the absolute value of negative x. Well, in this case, you have just negative x, and then absolute value, it doesn't matter if it's positive or negative x, your answer to the absolute value itself is just going to be the same, and so this whole thing is still minus whatever is the absolute value of x. And since this doesn't change this sign, it only changes the original, or the sign in the first term, then this one is also going to be neither odd nor even. This is the graph for number 9f, and that function says x plus, and then sine of x. And I think I'm going to need to zoom out to give you an idea of how totally cool this graph is. And if you look at the waviness, this little waviness here would rotate the 180 degrees and match up with this little waviness here, and all of the little waves that are created by the sine graph, when you add them to the linear graph, if f of x were x and g of x were sine x, and this is f of x plus g of x, you get this beautiful odd function because it's got rotational symmetry around the origin there at 0, 0. And this is probably the coolest graph in this entire packet. I love this graph. And then in letter F, f of negative x equals negative x plus the sine of negative x. Ooh, that sounds like an identity. So f of negative x equals negative x. Now, keep in mind that this identity, the sine of negative x, is going to equal negative sine of x, right? And so this whole thing is going to be minus sine of x. Well, both terms changed. Both terms changed sign. X became negative x, and sine of x became negative sine of x. If the whole entire function is negated, then this is going to be an odd function. So here comes the Algebra 2 infamous box problem. Let me just take a look real quick at the graph here, and I'll mark some things so that we can all agree on some numbers. Well, you're not here, so you can't agree, but I'm going to agree, and you'll just have to agree with me. But the important points on this graph are where I'm marking in red here, and I'm going to give those points some point values, and that way, if your point values are different by slight amount, 0.1 or something, then you can adjust your answers accordingly. Right here, this x-intercept, I'm going to say, is approximately -2.5. And this x-intercept over here, it's just a little less than 1, so I'm going to say it's 0.9. And then the y-intercept here, I'm going to call that -1, exactly -1. Now I've got the extrema. This one down here, I'm going to say is fairly obviously -2, -3. Let's not add decimals unless it's grossly off of a crosshair. So for example, this one right here, I'm going to call that -0.6, comma, -0.3. I don't care about the leading zero as long as I can find your decimal point. If you don't put a leading zero and your decimal point is too small for this old lady's eyes to see, then I'm going to mark it wrong. Just saying. And then this last extrema over here, this one, I'm going to call that 0.4 and -1.6. And let you take a look at that. And now that everybody in the room right here has agreed upon those numbers, those are the numbers that I'm going to use in the table. And so over here, then we said that now remember the zeros write as x equals. So the zeros, x equals -2.5, and we said +0.9. But your x-intercepts are going to have those same number values, and so your x-intercepts are going to be written as ordered pairs, -2.50 and 0.90. And then we said that the y-intercept was 0, -1. Now for this type of function, remember that you assume that there are arrows when the graph gets to the edge of the graph space. And this would be a x to the 4th graph, most likely, or it's definitely a polynomial graph. And so our domain is going to be all real numbers. The range starts at the extrema that's on the bottom, the very bottommost point on the graph. And we'll talk about relative and absolute min and max in a minute. But that point that's all the way to the bottom of the graph, the y value, because remember that range asks about y values, your y value is -3. And so the range of this graph starts at and including -3 and goes up forever to positive infinity. Now, don't get too messed up about increasing and decreasing. What I like to do is think it through from left to right, and I actually mark it. So I'm going to say this section right here, I know some teachers in Algebra 2 teach you to draw little arrows, but this section right here is decreasing, as is this section. I said I was going to go left to right, and I didn't, sorry. And then the sections that are increasing are here and here. And remember that you name increasing and decreasing on the x values. So it's not that it's going up to a certain y value, but that it changes direction at a certain x value. And now I'm going to work from left to right, and I'm going to say, look, it is decreasing from -infinity to -2. And for increasing and decreasing, it's always round parentheses. Then from -2 to -0.6, it's increasing. And then at -0.6, it changes again to decreasing, and it continues decreasing to +0.4. And then starting at +0.4, it increases to infinity. And that's the sorriest looking infinity symbol I've probably seen in a long time. There's no constant. A constant would be a horizontal line that's a part of a graph, and you would see that if it was piecewise, or an odd graph like the last one, the second last one, I think on the last page had a constant segment. If you turn back real fast, it was the graph for letter E, 9E had a constant portion. Anyway, remember the difference between the words relative and absolute, and we'll talk about those more on the next page, in fact. But relative is the idea of local, that right here I have a relative minimum because there are points to both sides of that -2, -3 that are above it. And this is a relative maximum because there are points to either side that are below it. And this is a relative minimum because there are points to either side of it that are higher than it. And so this graph has two relative minima and one relative maximum. And so back to over here, the two relative minima are that -2, -3, and the other one is the 0.4, -1.6. And then that relative maximum, just that one, is going to be -0.6 and -0.3. Now the word absolute has a very different sense to it. So an absolute minimum or an absolute maximum is what's the absolute lowest point on the graph. There's only one of those. The absolute lowest point on the graph is that point -2, -3. And again, I had to shut down for my clock. I don't know if you guys can hear that. It's funny because I stop every time, and it would be funny if you can't hear it. Don't tell me. And then if you look for the absolute highest point on the graph, well, there is none because that graph goes up and goes up and goes up and goes up forever. And so we're going to say that the absolute maximum, none, or NA. Don't use null set. I don't like null set. And then for end behavior, both ends of this graph are going up. Your end behavior in this unit is either going to be up or down, positive or negative infinity. And we'll get into what happens with end behavior of functions that have a horizontal asymptote or some other odd thing going on when we get into unit 7. So for now, positive or negative infinity, both ends are going up, so both answers are positive infinity. Now, for number 11, what I didn't say and should have is that I don't want you to have decimal answers. So no decimal answers. And really the idea here for the x-intercepts or zeros is to factor and set everything equal to 0. And then for B and C, you also want to find the y-intercepts. So for letter A, I'm going to factor this. I'm going to set everything equal to 0. And I'm going to start by factoring out a GCF that's x So I get 2x squared minus x minus 3. And now I'm going to factor that quadratic. I'm going to factor what's inside the parentheses. There are still a couple of you that are using slide and divide incorrectly, and I'm going to ask, please, if you can't factor this and you're using slide and divide, find some other way of factoring. I am going to assume that you can factor that. Pause it and take a minute and make sure that you factor it without just copying what I have. And I get x plus 1 times 2x minus 3. And the idea is that you set each one of those factors. So there's 3 factors here, right? We have the x, and we have the x plus 1, and we have the 2x minus 3. Set each of those equal to 0, and you get x equals 0, x equals -1, and x equals, and this one, if you're not sure, just set it equal, just write it out. 2x minus 3 equals 0, so 2x equals 3, and x equals 3/2. And so x is equal to 3/2. Please don't put 1.5. I just said that. Don't put 1.5. Now for B and C, you find the x-intercepts the same way as you find zeros. It's essentially the same thing. So here, for these x-intercepts, what you want to do is 0 equals x cubed plus 3x squared minus 9x minus 27. 4 terms, therefore it's grouping. Remember that you do grouping by looking at 2 terms at a time. So I'm going to kind of break that problem down into 2 separate GCF problems. And in the first one, I can factor out x squared, and I'm left with x plus 3. And in the second part, remember that you want to use the sign that's in the middle of the problem. And so my other GCF is going to be -9 times, and then it'll be x plus 3 again. If you take a -9 out of -27, you're going to be left with +3. And then when you're doing these grouping problems, remember that the 2 GCFs then make up your other binomial. And so here you've got 0 equals x squared minus 9 times x plus 3. Factor it one more step, and you'll have 0 equals x plus 3, x minus 3. And then bring down that other x plus 3. And so your x-intercepts, there are 3 of them. Set each of those factors equal to 0, and you get -3, 0, +3, 0, and another -3, 0. And then for y-intercepts, just make all the x's 0. That's fairly straightforward. So for y-intercepts, you're literally going to say y equals, and then 0 cubed plus 3 times 0 cubed, 6 squared, sorry, minus 9 times 0 minus 27. Well, notice that any term that had an x in it is just 0. So really you're just left with that last term. And so your y-intercept is going to be 0, -27. And then in letter C, again, I'm going to set the whole thing equal to 0. This is for my x-intercepts. And what's nice about this problem is that you can factor out both a 2 and an x. And that leaves me with a quadratic that does not have a leading coefficient. And then I want to factor just the quadratic part in here. And so that's going to be 2x times x minus 7 times x plus 3. And so my x-intercepts are going to be x equals 0. Remember that you have to look at the GCF if it's a variable. And it's not x equals 0. I'm going to get rid of that and say it's the point 0, 0. My apologies. So x equals 0 becomes 0, 0. Then x minus 7 equals 0 becomes positive 7, 0. And x plus 3 becomes negative 3, 0. So those are your three x-intercepts. And then again, for your y-intercept, you're going to substitute zeros for all the x's. So y equals 2 times 0 cubed minus 8 times 0 squared minus 42 times 0. Well, there's a 0 in every part of this now, so your y-intercept is 0, 0. So in this next part, you want to start by graphing each of these on your graphing calculator or on Desmos. And then you want to algebraically solve it to make sure that you have computed your zeros correctly. And notice that I don't want any decimal answers, which means if it's a radical, right, the radical is your answer, not the decimal. If it's a fraction, write it as a fraction and not as a decimal. Hint, A, B, and C, none of them have whole number answers. So algebraically here, after you have graphed this, replace f of x with a 0, and then 3 minus 7 over x. You're going to solve that equation. I would add 7 over x to both sides. So 7 over x equals 3. And remember, that's kind of like saying 3 over 1. And so 3 times x equals 7 times 1. And so for this problem, x is going to equal 7 over 3. For number 12a, and I am going to type in f of x equals, and then 3 minus, and if I just do 7 divided by x, it'll automatically separate that fraction for me. And with this one, because you're looking for the zeros, really you can just click on the function and then click on the place where you have the 0. It'll also do maxes and mins and y-intercepts in Desmos. Now remember that you don't want to give me decimal answers here. You actually want to show finding the 0 algebraically. But I kind of wanted to walk you through how you can use the graphs and the graphing function to help you verify what you have found algebraically. So although this says basically 2.333 or 2 1/3, if you divide 7 divided by 3, you'll get 2.3, and we found that the 0 here was 7 over 3. For part B, once you've graphed it, 0 equals, and then the other side of the function equation. I'll add 4 to both sides. And then when you're solving a radical, remember that you want to get the radical alone and then square both sides. And so in this case, 16 equals 5x plus 7. Subtract 7 from both sides, and so 16 minus 7 is 9. 9 equals 5x. Divide both sides by 5, and 9 over 5 equals x. Number 12b, so f of x is equal to, and then the square root of 5x plus 7. I'm going to right arrow to get outside of the square root, and then minus 4. And now, again, we're looking for zeros in this one, so click on the graph to select it, and then click on the point that is a 0. Remember that zeros are x-intercepts, and that is 9 over 5 that we found algebraically, and if you divide 9 divided by 5, you'll get 1.8, or 1 4/5. And here for part C, don't get lost in the fact that the problem looks really complex, because basically when you have a fraction set equal to 0, all you need is the numerator equal to 0 and the whole fraction equals 0. So when I solve a rational function equal to 0, I'm just going to take the numerator, set that equal to 0. The denominator can't be 0, so to solve this, you set the numerator equal to 0, and then solve for that x. And there's your answer for part C. 12C. Now there's a little quirk in Desmos as far as typing in a fraction that has more than one term in the numerator. You actually do have to type parentheses 5x plus 1 there, then hit the divide, and then go ahead and type your denominator x minus 3. If you are able to find a way to do that differently, please let me know. But I have not been able to find a way to do this without having to put the parentheses around the numerator. Now, I zoomed out a little bit so that I could see both parts of the graph. I see that I have an asymptote at positive 3 and at x equals positive 3, and another one at y equals positive 5. But I really don't care about any of that because I do just want to find the zeros for number 12. And so I'm going to zoom back in real close and click on the function, and then click on the x-intercept, and that's negative 0.2, and we found that that algebraically is negative 1/5. If you do 1 divided by 5, it's 0.2, so negative 1/5 is negative 0.2. Now, here's more of a conversation about relative and absolute maximum and minimum. And you really want to try to understand the concept that these are two very different things. The idea of relative, in fact, let me highlight this. So the relative min and max, I'm going to talk about with yellow, and the absolute min and max, I'm going to talk about with red. Okay. And with the idea of relative, remember that if there's a point that's a relative maximum or minimum, that means that in that one small section of the graph, immediately to the right and to the left of that point, every point immediately to the right and the left are either higher or lower. So in this case, this is a relative minimum because the points immediately to the right and to the left of it are both higher. This is also here a relative minimum because the points immediately to the right and to the left are higher. It's a relative minimum. And then there's a relative maximum here, and I wasn't going to use red. There's a relative maximum here because all the points immediately to the right and to the left of it are lower, and so this is a relative maximum. But Miss Applebacher, what about this point over here? What about that point? The thing about that point, it's not a relative maximum because it doesn't come back down again. There's no points to the left of that point, and so it's not a max. So this point here is not a maximum because there's no points to the left of it. And let's say relative. Okay. So I've only got 3. And so over here, let's make this list and say that my relative minima, there's 2 of them, the 0, 0, and the 3, 2. And there's that one relative maximum, and that point is 2, 3. Now that's all the stuff that I did in yellow. Absolute, again, I said it a minute ago, absolute means the absolute min, the absolute lowest point on the whole entire graph, just that one point that's lower than every single other point, that's the absolute minimum. And the absolute maximum is the absolute highest point on the entire graph. There's only one of them, and it's the absolutely highest point on the graph. So the absolute minimum, in this case, the lowest point on the graph, is also the relative minimum there at 0, 0. And so your absolute minimum in this case is the same as your relative minimum at 0, 0. Notice that here the graph keeps going up forever, and so there's not going to be an absolute maximum. Now let's look at this next graph because this is a little bit tricky as well. I'll start with the relative min and relative max. Okay. Here, you don't have any points on the other side or on the left of that point. So this is not a relative minimum. And here, same thing, it doesn't come back up to the right, and so this is also not a relative min. But there's nowhere else on the graph where the graph has points below a given point because, or above a given point, and so there's no relative minimum. None. And the relative max is interesting because although we want it to be 2, 4, there's no point there. It's a hole. And so this is also not a relative max. Because it's not a point. It doesn't exist. It's not part of the graph. 2, 4 doesn't exist as part of the graph. It's not a point on the graph, and therefore there is no relative maximum. Now I'm going to switch over to red and talk about absolute, the absolute lowest point on the graph and the absolute highest point on the graph. This point is the lowest point on the graph. The point exists. It doesn't matter if there's points to the left or right of it, but that point, 0, 1, is an absolute minimum. So 0, 1 is the absolute minimum y value on that graph. It's the lowest y value on the whole graph. But again, we've got this problem up here. The highest point on the graph you kind of want to be this 2, 4, but the point's not there. It's a hole. And so it's also, it's not a relative max, or it's not a absolute max. So it's not a relative or absolute max, even though if there were a point there, 2, 4 would be both. It's not a point, and therefore it's not either. And so over here, absolute maximum, none. The highest point does not exist. Now, these next 2 problems ask you to do function operations. And so you're going to add, subtract, multiply, and divide functions. Remember to look for restrictions on the domain of your answer, and sometimes the restrictions on the original functions will trigger a restriction on the domain of your answer that you weren't expecting if it weren't for the fact that it's a function that's created by operations on two other functions. So here we go. For example here, f plus g of x is really just saying f of x plus g of x. And so here we have f of x equals 1 minus 3x, and g of x is equal to 5x cubed. And if you really want to write it in standard form, put the 5x cubed first and then minus 3x and plus 1. And that's f plus g. There were no restrictions on the domains in f of x or g of x before you started the problem. And there's no restriction on the function that we have here because it's a cubic function and there's no denominator, there's no logarithm, and there's no radicals, so there's no restrictions on that domain, and therefore your domain is all real numbers. In this next one, your addition and subtraction are often going to feel like very similar problems. So here we have f of x minus g of x. Just remember to distribute minus signs if you need to. F of x is 1 minus 3x, and then g of x minus 5x to the third power. And again, if you want to rewrite that in standard form, negative 5x to the third power minus 3x plus 1. And again, there's no denominator, there's no radical, and there's no logarithm. Therefore, your domain is all real numbers. In letter C, you want to multiply f of x times g of x. And f of x is 1 minus 3x, and g of x is 5x to the third power. And I'm going to distribute because you don't want the parentheses in your answer. And so this is going to be 1 times 5x cubed is 5x cubed minus, and then 15x to the fourth. And again, if you want to write that in standard form, pull that the term with the higher exponent out, 15x to the fourth plus 5x to the third. And again, no restrictions on the original f of x or g of x domains. And x to the fourth plus x to the third is a polynomial function, and there's no denominator, logarithm, or radical, and therefore your domain is all real numbers. And last but not least, division, which often triggers a denominator because this is going to ask us to do f of x over g of x. And so in this case, we've got 1 minus 3x all over 5x cubed. And we have to restrict the domain here because 5x cubed, remember your thinking here is that 5x cubed cannot equal 0. Divide both sides by 5. X cubed cannot equal 0. Therefore, x cannot equal 0. And so your domain for this one is going to be negative infinity to 0, not including 0, and then 0 to positive infinity. Now in number 15, you want to be careful because in your original given functions, g of x has a denominator and the x can't be 0, so you need to remember that there's a restriction that in all four of the operations, the addition, the subtraction, the multiplication, and the division, you cannot have an x value that's 0 in your answer, even if it's okay based on what the function says. You can't substitute x as 0 because it was one of the original, it was restricted from the original functions. Ms. Applebacher, what are you talking about? Well, here, this is what I'm talking about. So in this first one, we're looking at f of x plus g of x. And f of x then is 2x squared minus 5. And g of x is 7 over 3x. There's no way to simplify that function. That's your answer. And then the domain is restricted because of the 3x denominator, and therefore your domain is going to be all numbers except 0. So negative infinity to 0, not including 0, and then 0 to positive infinity. The subtraction is going to be similar. So for this one, your f of x minus g of x is going to be 2x squared minus 5 minus 7 over 3x. And again, that can't be simplified. That's your final answer. But you have to keep in mind that that 3x as a denominator is going to impact your domain. And so your domain here is negative infinity to 0, not including 0, and then 0 to positive infinity. So your addition and subtraction of functions for this problem are also going to be similar. Be careful with the multiplying and dividing and the fraction. The 7 over 3x gets a little bit funky here. So with the multiplying, so here we are, we're going to do f of x times g of x. And so the f of x is going to be the 2x squared minus 5, and you're multiplying that by the g of x, which is 7 over 3x. And again, I'm going to distribute that ugly fraction to both terms inside the parentheses. And so 7 times 2x squared is 14x squared. 5 times 7 is 35. And that whole thing can be written over 3x because you're just distributing the numerator, the 7 times the 2x squared minus 5. Now, the problem that is as simplified as it can be. The problem is, once again, that your denominator has 3 times x, and so we need to take that into consideration for our domain, which then is going to be negative infinity to 0 and 0 to positive infinity. And then in the division at the end here, remember that the division is telling us to do f of x in the numerator and g of x in the denominator. And so this gives us 2x squared minus 5 all over, now all over 7 over 3x. But remember that that's a division problem, right? And so let's write that over here. I'm going to rewrite that as 2x squared minus 5, and it has to be the quantity 2x squared minus 5, divided by 7 over 3x. Well, that is the same as 2x squared minus 5 times 3x over 7. Remember that when you're dividing by a fraction, you take the reciprocal of the fraction, the second one, and flip it over and treat it as a multiplication problem. So now I'm going to take just the 3x, and I'm going to distribute it through the 2x squared minus 5. So in the numerator, I get 6x squared minus 15x, and my denominator is just 7. But be careful here. You don't have an x in the denominator, and if I gave you this and it wasn't a division problem and I just said what's the domain of that function, you would say, well, it's all real numbers because there's no x in the denominator. The problem is that at the very beginning of the problem, g of x, one of the two functions that you're using for your operations, has the restriction that x cannot equal 0. So you have to do this whole entire problem assuming that x cannot be 0. And therefore, in the domain for your final answer, you still have to say that that domain is restricted to all numbers except 0. So put a little star next to that one and make sure that you understand why the domain for number 15D is slightly different. Now, for these last 3 problems, you want to graph them. And remember that the question is asking if it's 1 to 1, and you can't compute the inverse of a function if it's not 1 to 1. 1 to 1 means that it's a function, therefore it passes the vertical line test, and it passes a horizontal line test that works the same way as a vertical line test. This is number 16, and really all I want to do is decide if the functions are 1 to 1 based on the horizontal line test. And so I'm going to go ahead and type it without the f of x, but negative 2x to the 3rd power plus 4x to the 2nd power, and then minus 3. And if you were to graph or draw a horizontal line through this middle part of the graph here, it would touch the graph more than once, and therefore it does not pass the horizontal line test. Therefore, it's not 1 to 1, and therefore it's not a function that has an inverse function. So for example, this first graph is going to look something like this, and if it's a function because it passes the vertical line test, but it's not 1 to 1 because it doesn't pass a horizontal line test. Therefore, this is not 1 to 1, and therefore no inverse function exists. B, and this is another one where I have to kind of cheat the numerator by putting parentheses and then hit the divide sign, and 3x minus 2 for the denominator. And then let's take a look at the whole graph. So if I look at this graph in terms of what I know about rational functions, I've got a horizontal asymptote right here. That's based on the denominator, and so that would be a horizontal asymptote where the denominator equals 0, and that's 2/3. I also have a this is a vertical asymptote where the denominator equals 0, and the vertical asymptote is positive 2/3. There's a horizontal asymptote here, and that's about the degree and the leading coefficients, and we'll get more into that in Unit 7, but just know that the horizontal asymptote is y equals 2/3, and that's right here. So there's nowhere where this function would fail the horizontal line test, therefore it is 1 to 1, and it does have an inverse function. Whereas in this next graph, when you graph this one, you're going to get a graph that looks sort of more or less like this, and that both passes the vertical and the horizontal line test. So yes, it's 1 to 1, and thus an inverse function exists. C, and again I'm going to use the parentheses to give myself the numerator, and then I've got 2x to the second power minus 5 in the denominator. I'm going to zoom in just a little bit. I don't need to be that far zoomed out from the last graph, but notice that there are a lot of places where if you draw a horizontal line, it'll hit the graph twice. Therefore, it's not one-to-one, and this function does not have an inverse function. And in this last part, letter C, when you graph that, and I'm going to try to put some Desmos graphs in this video, so you may be wondering why I'm drawing them if you've already seen them on Desmos. But in this last graph, it's going to sort of kind of look like this, and like this, and like this. And it fails the horizontal line test here and here, where it goes through the graph more than one time. And therefore, this is not one-to-one, and therefore, no inverse function exists. Okay, last page. So first of all, we're going to look at composition of functions. And I think that I have given you guys enough space to work out these problems. The last one might be a little squishy, so give yourself some small handwriting there, but the first two should be just fine. Each of these problems you're asked to do f of g, and remember that this f of g of x, that little circle there, which is not a dot but a circle, is the same as saying f of and then g of x. So you're going to take whatever is the g of x and you're going to put it where the x is in the f of x. And so that whole thing for this first problem, you're going to be doing f of and then that negative 3x squared. And so in this case, it's going to be 5 over negative 3x squared. And that's it. That's your expression. That's the answer. Now, you can't have a zero denominator, and the directions ask you to comment on the domain, even though I didn't put a little spot for it. So just tell me here that your domain is going to be all real numbers except 0. In the second problem here, remember that f of g is the same as f of g of x. And so we're looking for f of, and then this radical 4 minus x. And so that's going to be 7 times radical 4 minus x squared minus, and then radical 4 minus x again. That's kind of messy. So the first thing you want to do is look at where there's parentheses, and anything with a radical and then squared just gives you what was inside the radical. And so here I get 7 times the quantity 4 minus x, and then minus, you can't simplify that radical at the end in any way. And so your answer to this whole thing is going to be distribute the 7, so 28 minus 7x, and then minus that radical 4 minus x. Can't be simplified farther. But remember that you can't have a negative inside of a radical. So for your domain, you want to keep 4 minus x greater than or equal to 0. And so 4 is going to be greater than or equal to x. And so your domain here for this problem, domain is going to be negative infinity to that positive 4 that we just computed, including the 4. And for this last problem, f of g is equal to f of g of x. And remember that I said you might come close to running out of space, so I'm going to make this a little bit smaller. So I've got f of 2x plus 1. And I also have a lot of space on the sides of my screen that you don't have on your paper. And so f is 5x minus 3x squared, so that's going to be 5 times. And then whatever this quantity is, I'm going to substitute where the x's were in f. And so that's going to be 5 times the 2x plus 1. And then minus 3 times the 2x plus 1 squared. And what I'm going to do is I'm going to simplify 2x plus 1 squared first. And so I'll leave alone the 5 and the quantity over here for now. 5 times 2x plus 1 minus 3 times. Now I'm going to square 2x plus 1, but I have to FOIL it, so that's 4x squared. And then plus 2x is plus 4x. And then 1 times 1 is just 1. So that's the answer when you FOIL. And then the next thing that I'm going to do is distribute the 5 and the minus 3. And so over here, I get 10x plus 5. And then over here, I get minus 12x squared minus 12x minus 3. And then when I simplify that, I'm going to rewrite it in standard form. And that whole thing ends up becoming negative 12x squared. And then I've got the 10x and the minus 12x, so that's going to be minus 2x. And then the 5 and the minus 3 is going to be plus 2. So that's your answer. It's not pretty. And for the domain, if you look, there's no denominator, radical, or logarithm in f of x or g of x. And there's no denominator, radical, or logarithm in my final answer, and therefore my domain here is still going to be all real numbers because there's no restrictions on the domain. Now, for number 18a, when you graph that, it fails the horizontal line test. So don't compute an inverse function if it fails the horizontal line test, therefore it's not one-to-one. No inverse function exists because it is not one-to-one. The graph for number 18a, and we want to see if it has an inverse function first, and if it does, then we'll compute it. And so what you're looking for here is if the function is one-to-one, if it passes the horizontal line test, and 18a then does not pass the horizontal line test. So we're going to move right along to letter B, 18b, and the function is radical 2x minus 5. And as you can see, this function does pass the horizontal line test. There's nowhere you could zoom out and zoom out and zoom out, and I just zoomed in. Why did I say zoom out? And you can zoom out, you can zoom out, and you can zoom out, and it's never going to fail the horizontal line test. Therefore, this function does have an inverse function. Another thing that I wanted to show you about using Desmos with the inverse functions is that if I graph my original function as y equals, and then the function has an x in it, and I want to see how the restricted domain works on the inverse function, notice that the domain of this function starts here at this x value 2.5 and goes to positive infinity, but the range starts at 0 and goes to positive infinity. And remember that when you're graphing or talking about inverse functions, you switch the domain and the range. So let's say that I wanted to graph the inverse function. I switched the x and the y, but with Desmos, not with the graphing calculators in class, but with Desmos, you can type in this equation with the x and the y switched. So I can type x equals square root of 2y minus 5. I'm going to make that red. I tend to like to graph the inverse functions with the original function blue and the inverse function red. But what you'll see here is, although algebraically you end up with a x squared function, you have to only use the domain from the original function's range. So the range here is 0 to infinity. The domain of your inverse function is going to also be 0 to positive infinity. And so you've got the restricted domain here. Letter B is 1-to-1. And so here, I'm going to change f of x to y. So y equals radical 2x minus 5. And then I'm going to exchange the x and the y. So instead of y, I write x. Instead of x, I write y. And then I'm going to solve this equation. I want to get the y by itself. So I'll start by squaring both sides to get rid of the square root. And what that gives me then is x squared equals, and then the square root goes away, so 2y minus 5. So now I've got x squared plus 5 equals 2y, and divide both sides by 2, and I get y equals 1/2 x squared plus 5/2, and really I should write it f inverse of x equals 1/2 x squared plus 5/2. Now, here's the tricky part with this one, because it does say find any restrictions on the domain. And remember that if your original function, this, had a restriction on the domain, the original function here was a function that looked like this, and the range of the graph starts at 0 and goes to positive infinity, and the range becomes the domain of the inverse. And so your domain here is going to be from 0 inclusive to positive infinity. And hopefully I will be able to work in a Desmos graph on this video. And you'll be able to see it. Now, for this letter C, you might need a little bit more space. That goes with number 18C, and the fraction is 4/7 minus x. Clicking on home kind of brings you back to the middle of the graph, and then I can move it around as I need to. And you've got a vertical asymptote where x is equal to 7. You've got a horizontal asymptote where y is equal to 0. There's no place where this graph fails the horizontal line test. So it does have an inverse function. It definitely has, it's 1-to-1, and it definitely has an inverse function. And so y equals 4 over 7 minus x, and x, then exchange the x and y, equals 4 over 7 minus y. And then I'm going to multiply, remember that you're thinking about this as x over 1. So I'm going to multiply x times 7 minus y, and 4 times 1 is 4. But then what I'm going to do is I'm going to divide both sides by x, so that I get 7 minus y stays on the left, and then divide by x, so 4 over x. And then I'm going to add y to both sides and subtract 4 over x from both sides, and I end up with 7 minus 4 over x equals positive y. And so your answer here is f inverse of x equals 7 minus 4 over x. And your restriction on the domain here is that x cannot equal 0. And so you've got negative infinity to 0, not including 0, and then 0 to positive infinity. And then in this last one, for number 18D, and again, I have to use the parentheses for the numerator because it's got more than one term, and then then hit divide to get the denominator. And I'm going to use my little magic keyboard to bring the absolute value goalposts up, and then type in the 5 minus x. And this is really kind of a strange looking graph. I'm going to zoom out just a little bit. I hope that it's obvious that this fails the horizontal line test pretty much everywhere until you get down here, that you draw a horizontal line. It'll hit the graph more than once. I had a stray mark. In this last one, if you graph this, you'll see that it's not 1-to-1. It's not 1-to-1. Therefore, no inverse function exists. Now, in this next section, you're going to do composition of functions again, and it says, look at how the wording is. It says to show algebraically that. And basically what that means is that I'm telling you, yes, these two functions are inverses of each other. And what you're going to do is use algebra to prove that I'm telling you the truth, basically. It was like when we did proving trig identities, where I would give you an equation and you would use the trig identities to verify the equation that I told you is true. I'm telling you it's true already, and you're just proving it using algebra to show that. So, for example here, what you're going to want to do is do both f of g and g of f. And so, excuse me, if both of those equal just x, both f of g equals x and g of f equals x, then the two functions are inverse functions. Hint, that's what you should get for both of these problems, A and B, and both f of g and g of f, because I'm telling you already that they're inverse functions. You just need to show me the algebra steps. Don't do it in your head and say, yeah, they're functions, obviously, I hope. Anyway, so here, f of g of x, and they're going to be a little messy now. You're going to take g of x, and you're going to substitute in these two places where we have f of x. And so that's going to be in the numerator 3 times, and then that big fraction, negative 2x over x minus 3, and then in the denominator, that whole big fraction again, negative 2x over x minus 3, and then plus 2. Now, in the numerator, I'm going to multiply, but remember that when you multiply a whole number times a fraction, you only multiply the numerators. And so that big fraction is going to have negative 6x in the numerator and x minus 3 in the denominator. That's your numerator. And down here, what I'm going to do, I want common denominators, so I'm going to multiply this by x minus 3 over x minus 3. And so I've got that minus 2x over x minus 3 plus 2 times x plus 3 over x minus 3. Unlike you, I probably have a lot more space left over here. So now I'm going to look at my denominator, and I'm going to do that addition. I'm going to leave the numerator where it is, so that's negative 6x over x minus 3. And then in the denominator, I'm not going to simplify it completely, but when I do that now, I have negative 2x plus 2 times the quantity x plus 3. Why did I put plus? It really is minus here. Excuse me while I fix this. So this is a, my apologies. This is a minus here, and therefore it's also a minus over here. X minus 3. And that whole thing over that common denominator, x minus 3. And notice that now I have a complex fraction, and I've got a numerator divided by a denominator, and they both have the same denominator, so those cancel, which is sweet, because now I just have my numerator, negative 6x, and my denominator, negative 2x plus, and now I'm going to do that little distributive property here, and that becomes plus 2x and minus 6. And isn't that nice, because negative 2x plus 2x, those two cancel, and now I have negative 6x over negative 6, which equals x, and that's the first composition that I need to prove that those two functions are inverses. Sorry that it's small. Just want to make sure it all fit. I think I was a little extreme over the top here. But then my next one, I'm going to do g of f of x. It's equally tedious, and the sound you're hearing in the background, I don't know what the weather's going to be like when you watch this video, but I'm doing this on a snow day, and so you can hear the snow plows out in the street. So between my clock and the snow plows out in the street, it's no better than trying to do the videos at school with the bell ringing in the background. Oh well. So g of f of x, I'm going to substitute, this time I'm going to substitute 3x over x plus 2 into the two x's that are in g of x. So what I'll get there is numerator negative 2 times, and then that fraction 3x over x plus 2, and then the denominator will be that same fraction 3x over x plus 2, and then minus 3. And again, I think I was a little over the top here, and I'm gonna get rid of part of my fraction line so that I have more space. And then I'm going to multiply. Again, I'm going to only multiply that negative 2 times the numerator, because it's like it's negative 2 over 1. And so my numerator is going to be negative 6x all over x plus 2. And then for my denominator, I want like common denominators, and so I want to multiply that by x plus 2 over x plus 2, so that now my common denominator is this x plus 2. And I've got 3x over x plus 2, and then minus 3 times x plus 2 over x plus 2. So now in the denominator, I've got this subtraction problem, but I've got common denominators, so I don't have to change anything else. And then I have in my numerator negative 6x over x plus 2. I'm not going to simplify the denominator all the way yet. And in the denominator, I have 3x minus 3 times x plus 2 all over x plus 2. And again, now I have a complex fraction. I have a numerator and a denominator, and they both have the same x plus 2 in the denominator, so I can cancel those. And then that whole thing is negative 6x all over. Now I'm going to simplify 3x minus 6. Oh, look, I've got 3x minus 3x, so those cancel. And now I've got negative 6x over negative 6. The negative 6 is canceled. That whole thing is equal to x. And so I have proven, oh, I made that even smaller. Ugh. Because then I commented on it, and then it just got smaller and smaller. Again, my apologies. But end of the day, f of g equals x, and g of f equals x, and therefore you have proven that f and g are inverse functions. And now I'm going to do that whole process again with all these cubes and cube root things over here. This is not going to be as hideous as part A because you don't have the complex fractions. So let's come over here, and I'll start with f of g. So f of g of x. I have to have enough parentheses. I'm going to take this cube root here, and I'm going to put it where the x is right there. And so that becomes 2 times, and now this cube root of numerator is x plus 6 over denominator 2 cubed minus 6. Now here's the cool thing about this problem is that you have a cube root cubed. Cube root cubed just gives you what's on the inside. Don't forget to use parentheses. So now I've got 2 times x plus 6 over 2 minus 6. Well, look at that. The 2's cancel, and so that whole thing just equals x plus 6 from the numerator minus 6 from outside the parentheses, and all of that just equals x. Boom. And then I'm going to do the g of f of x. I'm going to do the other composition. So g of f of x means that I'm going to take the function f, and I'm going to put it right there where that x is in g. And what that's going to look like is big monster cube root. Take that 2x cubed minus 6, put it where the x is, and then plus 6 over 2. And now plus 6 and minus 6, well, yeah, those cancel. And so now I have big cube root 2x cubed over 2. Well, now the 2's cancel. And now I literally just have the cube root of x cubed. The cube root of something cubed is just that something, and so that whole thing equals x. And once again, to prove that they're inverse functions, you need f of g of x, equal x, and g of f of x equals x. and therefore I have proven that those two, f and g, are inverse functions. And last but not least, the two graphs at the bottom. Letter A is a little bit dicey. Try starting with the asymptotes. So if this original graph has an asymptote at y equals 0 and x equals 2, I'm just going to take those asymptotes and I'm going to switch them. So I'll have in my inverse graph, I'll have asymptotes at x equals 0 and y equals 2. So when you're looking for points, the original graph has points at 0, -1 here, and 1, -2 here. And just take those 2 points and reverse the x and y values. So instead of 0, -1, it's -1, 0. And instead of 1, -2, it's -2, 1. And so my inverse graph that I'm going to draw in red, look at the green asymptotes and those points. And there's one part of that graph. And then the upper part of the graph goes through the point 4, 1, and it goes through the point 3, 2. So I'll graph a point at 1, 4 and 2, 3. I'll look at my green asymptotes as guidelines. And I know that's a little crazy, but the red, I'll highlight it for you. The red is your inverse function right there and right there. Part B is not so crazy. Look at the points that you know. So there's a point at -2, 1, -1, 2, at 2, 3, and how about at 7, 4? I don't think I can graph the inverse of that, but -2, 1 becomes 1, -2, and -1, 2 becomes 2, -1, and then 2, 3 becomes 3, 2, and I can't graph the 7, 4, and so then I'm just going to graph this, and there's my inverse function. And if you kind of want to eyeball it, remember that it should look like a reflection over the line y equals x. And that is the line y equals x. And there you have it. You are now ready to take the Unit 6 test.